I wish I could talk more broadly about accelerators, but I'm mostly going to talk about graphics processing units. We've started working with Intel's accelerator, but I don't have a good story to tell about that yet. So I'm going to delay judgment and focus almost exclusively on GPUs, but also be a little bit more forward-looking. So we have some existing ways to program GPUs, but I want to talk about some more abstract, more generic ways of thinking about programming these massively parallel devices. Right. So here's the reality check. We've got 3 hours, which sounds like a lot, but it really isn't enough to get really into the weeds of GPU programming. You're not going to walk out of here as GPU gods or goddesses. It's just not going to happen. However, I hope you'll get an appreciation of what is the state of the art, what are the possibilities, and unfortunately, what are the landmines buried shallowly beneath the surface when working with GPUs. We'll discuss some basics. I'll have lots of links. You should be able to download these slides already from the website, and there are lots of clickable links to get you to more in-depth information. And I was hoping to have a hands-on experiment, but we have a couple of technical issues. I don't have access to the 2-key cluster. I think you guys do have access. So if you can get onto the cluster and get an interactive job running, then you might be able to do some hands-on experiments. How many of you have got laptops with discrete GPU units? Okay, so you guys, you should make sure you can install NVIDIA's, are they NVIDIA GPUs? The 4 of you, make sure you've got the CUDA SDK installed. We have solutions for the people with AMD discrete GPUs as well. We'll hopefully cover some more bases. But hopefully we'll get all of you to at least compile and run a GPU program by the end of the day, hopefully, or end of the morning, fingers crossed. There are just unbounded resources on the web for learning about GPUs for self-directed study. There is even a 21-hour course. It's a Udacity course. I've looked at some of it. It's fairly straightforward material. If you've got 21 hours to spare. I've created a couple of GitHub repositories which have some example codes that we'll refer to during this session. One specifically with some simple codes at this GitHub, and we've got another GitHub for something called Ocker, which we'll describe later, which I'm going to try and persuade you is a way to transcend the divisions between OpenMP, and you've heard a lot about OpenMP, NVIDIA's programming language for GPUs called CUDA, and the OpenCL standard. We're, as my research team and collaborators, are desperately trying to hide all that stuff behind the scenes. And Ocker is our first attempt at pushing all that stuff back into behind the scenery so that we can just generically program pretty much any device with any of these programming models, but just writing one program, which will cross-compile to any of these different platforms. If you download the slides, you should be able to just click on that link. And there's a backup copy. I think that's out of date, that top link. OK, so here's how we'll structure the session. I'll talk a little bit about my research group and what our interests are. Then I'll start talking about processor architecture trends, and specifically, what is the difference between a CPU and a GPU? And nowadays, it's actually becoming vanishingly small difference between a CPU and GPU. But we'll just highlight some of the design decisions that were made when NVIDIA AMD started building GPUs. What is it that drove the architectural structure of these devices? Then in this part 2, I'll talk about how do we program NVIDIA's GPUs using CUDA. And one of the things that might survive long-term from NVIDIA's CUDA model is the offload programming model and their threading model. These are actually very interesting aspects of what NVIDIA has done. And I'll give you an example with a simple Poisson solver as a sort of a slightly non-trivial example of how to program with CUDA. I'll briefly dive into issues with optimizing code for GPUs. It turns out that it is not entirely straightforward to program GPUs. And I'm underplaying that statement a little bit. However, I also will claim that strongly optimizing CPU code is also an art. It's just by self-selecting to program for GPUs, you care about performance. And in order to get good performance out of a GPU, you really have to pay attention to quite a few details. Now, CUDA is NVIDIA's programming model for programming GPUs. And that's great if you're one of the 3 people in the room who's got a GPU, an NVIDIA discrete GPU on your laptop. A bunch of other of you have got AMD's GPUs, discrete GPUs in your laptop. In fact, that's been the trend. Various manufacturers laptop manufacturers either take AMD or NVIDIA, or they switch, depending on which manufacturer they can get the best deal from. So it's in my viewpoint, I introduce programming GPUs with CUDA because it's the easiest way to get started, but then I'm going to play a bait and switch because you shouldn't really program in a single vendor language, in a vendor-locked language. And CUDA, by its nature, by design, is very much geared towards NVIDIA's hardware. So I will generalize a little bit and talk about the open computing language, OpenCL, which can be used to program the NVIDIA discrete GPU, the AMD discrete GPU, the Intel CPU, which is interesting because you can treat your Intel CPU as a multi-core OpenCL device. Suddenly it's interesting, right? Now you can write a code that can run on the NVIDIA GPU, the AMD GPU, or the Intel CPU. So it's designed for portability. And then so you'd think that would cover all the bases. You think, okay, now I can program everything, we're done, go and program. Well, there are some interesting market forces that mean that OpenCL may not be the best solution on any single platform. It will allow you to program at a platform, at an AMD device, or at an NVIDIA device, or at an Intel device, but you might be able to get better performance by using the vendor-preferred native solution. So for Intel, you might consider OpenMP, or in fact OpenCL. Intel's OpenCL on their CPUs is actually a pretty good solution. On NVIDIA's hardware, you might take the native choice and program with CUDA. AMD, you take effectively the native choice and program in OpenCL. So then I've told you we've got 3 different solutions floating around, and anybody who's written any substantial amount of code will recognize that they don't want to have 3 implementations of their code inside their code. It's a nightmare to maintain. You change one implementation, you're going to break something in the other implementations. So what we've done as a group, research team, is we've developed Ocker, which actually doesn't stand for anything. It just sounds cool. Originally, I'll be honest, originally it stood for OpenMP, CUDA, OpenCL, and OpenACC. It's also ACC backwards, if you look at it. Unfortunately, when we tried to wrap OpenACC behind the scenes in Ocker as a model which you could program with generically in an abstract way, turns out that OpenACC at that point was not mature enough to be on a level footing with the other programming paradigms, OpenMP, OpenCL, CUDA. The compilers weren't there. There was no freely available compiler. So it should really be awk at this point, but that's okay. Right. Now, I have a research team. We take GPU programming very seriously. They're all experts in some aspect of numerical PDEs, but simultaneously, they're all GPU-enabled. They all know, because at some point, we didn't know what was going to be the successful dominant paradigm in programming these many-core devices. They all know OpenMP, they all know CUDA, they all know OpenCL, okay? But now they all know Ocker, and they all program in our Ocker model, because none of them want to write 3 implementations to get best performance on any given platform. So we've successfully abstracted all our codes into this Ocker framework. We focus on numerical, basically fundamental numerical methods, approximation theory, numerical discretization PDEs, and today I'm really focusing on our acceleration experience. So really I'm relating to you more or less our user experience of programming GPUs, and of the whole GPU verse we're telling you about. I'm trying to tell you about the parts that were important for our applications. There is quite possible that I won't touch on things that are important to you, and I'm happy to talk with people on the breaks afterwards if you have specific questions that aren't covered by the material today. And we push to applications. So we push to computational electromagnetics, tsunami modeling, gas dynamics, global scale seismic modeling. This was a 2010 calculation, which was an adaptive seismic calculation on an Earth scale model. 40 billion degrees of freedom running on, and this is funny. So there's a large computing system at UT Austin, and it's large enough that it has its own dedicated GPU cluster for rendering the results that come off the big cluster. We hijacked the rendering cluster and got better performance out of the rendering cluster than they typically get out of the actual big iron system. Of course, we didn't have very long to do it, because they basically would take it down for maintenance. We got 12 hours to get on there, get the results, get off. But we actually were able to do that. And this was part of a submission to the Gordon Bell Prize in 2010, so it was a runner-up. We got beaten by a fast multipole method, and if you know those methods, we'll always get beaten by those methods for various reasons. Okay, so let's talk about trends. Does anyone have any questions just before I rattle on? Nope, you're good. Okay, so this probably seems obvious maybe to most of you, but if you think about what are CPUs designed for, essentially way back when, they were designed for word processing, spreadsheets, very simple, even running on MS-DOS or on not even with graphics. The design, that purpose drove a good deal of the design philosophy that was pushed into the early x86 design. The primary focus was on making sure that single threads run very fast. You don't want the thread to stall. You don't want the program to stall. We have always been faced with faster processors than memory. So as the curves of performance of processors and performance of memory diverged, CPU designs included a good amount of cache, ungodly amounts of cache, and special units on the device which are there to predict and speculate about what that thread's going to do next. Bring or prefetch data in from the machine memory into cache, and everything was focused on making sure that these threads don't stall, okay? If you look at the structure, I'm not going to dwell on this very long, but if you look at the structure of the sort of a primitive x86 core, what does it consist of? So There is a control unit, which is driving the game. There's an internal bus over which data flows. There's a register file, which keeps the context, basically keeps the variables stores the variables. And then we've got a couple of different ALUs, arithmetic logic units. One involves forming addresses for memory queries. One is involved with actually processing data. So this is a very rudimentary overview of what the core on one of these processors looks like. Okay? And I'm going to claim that to be a core, you're going to need to have your own independent control unit. You're going to have your own independent stream, okay? Which is going to be at variance with what NVIDIA thinks a core is. So we're going to define a core as a piece of silicon which includes a control unit, which includes its own independent instruction stream. What's the arithmetic logic unit? This is unfortunately what NVIDIA will call a core, but it's not, because it doesn't have its own instruction stream. It does, however, take two inputs, and will give out an output based on the operation. So it'll take 3 inputs, the operation and arguments, and it will put out a result. Okay? And there's a few different ALUs. There's floating point ALUs and address ALUs for doing address point arithmetic. Okay. So it's very basic CPU 101. Now, if we look at a typical, sort of abstracted, typical modern CPU style core, as I've stated, the design is to emphasize the performance of an individual thread. There's an instruction fetch decode unit. That's basically pulling instructions in. There's an arithmetic logic unit that's basically executing the commands, and then we have some context for that's basically things like registers that need to be fed into the ALU. To keep the core busy, it's doing a number of things. It's doing branch prediction, it's doing out-of-order control logic, trying to see if can I do this operation first, or can I do this operation first, and then sequencing, pipelining those operations to try and make sure that it's busy at all times. And there's a significant amount of space used for prefetching data, in fact, prefetching operations, so that this thing will not stall, or try and avoid stalling as much as possible. And a big-ass data cache to try and stop stalls happening. Okay? So we want to make sure we've got operations that can be done, and data that those operations need at any given time for the thread to continue processing. Okay. So what is the impact in terms of processor design? So if we look at this is a fairly old Isaiah 2008 CPU die shot. And here's the actual original. You can see, so there's actually a sort of a, well, the internet is great. Some people say the internet's for porn. I say the internet's for downloading die shots. These are just beautiful things. We'll see some better examples later on which are colorful. But anyway, right. So of all this floor space on the processor, this part down here is the floating point unit. That is the worker. Everything else is management and logistics, right? That's the graduate student. Everything else is the university. It's administrators, and we all love administrators, right? I would prefer to populate this whole chip with grad students than I would administrators, okay? He's not there. He's at a conference. Okay, so from an HPC perspective, this is kind of nuts, right? that we've got this incredibly expensive piece of silicon sitting and inside in itself another organization, and on this chip we're spending so little time with the actual part that we care, or little space on the part we care about. Unless you're sorting strings for DNA matching, you're typically working with floating point numbers. Everything boils down to ax plus b, multiply adds, okay? Oh boy, so that's sort of the state of the art in CPUs. A lot of management, a lot of infrastructure designed to make sure that threads don't stall. Okay? The GPU world is rather different. The GPU world, what is the task? This is a rendered image. This is not a real person. Every pixel on here is the result of a calculation, and all those calculations are independent. Okay? There's an internal model, which is basically a triangulation of this guy's head, triangulation of the background, and on the triangles in the triangulation, there is a texture, which gives you some of the sub-triangle scale details in this face. There may also be a bump map, which gives you some deviation from a planar triangle of the points on the surface of this person's face. Now, to render this requires basically the same set of calculations at every pixel, because you basically have to say, how do you project these triangles down onto a planar surface? It's basically a lot of geometry. So early on, ATI, NVIDIA, realized that they could accelerate this process by designing custom hardware, which was specifically designed to quickly and in a massively parallel way do these operations in groups of pixels. Okay? So what are the design goals for the GPU? They're rather different than the CPU. The CPU is all about that thread, that godlike thread that has to keep going, right? On the GPU, it doesn't matter what order you render those pixels, as long as they arrive on the screen within a 60th of a second for a typical first-person game. That's the target. It doesn't matter. The primary, no pixel on there is more important than any other pixel in that picture. So render them in whatever order you like. If you've got a thread that's working on a pixel and it stalls, fine, as long as some other thread is working and computing on other pixels. Okay? So I chop that picture into pixels, and as long as all the pixels arrive in a 60th of a second, fine. Doesn't matter in what order they arrive. So that's going to change the way that the chip is organized and the design of the architecture of the chip. It really is a completely different viewpoint on what this device is for. We still have issues with memory latency, but instead of, and this has changed over the years, but instead of having big-ass caches, we're going to just use massive parallelism over provisioning, so just massive number of threads that can hopefully hide some of the latency. So if you've got thousands and thousands of threads, you may be executing 500 of them at any given time. The ones that are stalled because the data hasn't arrived from the main memory, fine. We'll just let them stall. Okay? So we're going to hide latency by just massive parallelism. So the original early GPU designs, there's always this constant push and pull between programmers and hardware designers. NVIDIA managed the following trick. It said, okay, well, we've spent the 90s making the compilers really good, so on the CPU. And a lot of stuff in terms of pipelining, scheduling, caching, and everything is hidden away from the programmer. But NVIDIA managed this trick. They said, if you're willing to manage the memory yourself, you can get good performance. That's a really clever trick, because they're appealing to the ego of GPU programmers that says, well, if you're a good programmer, you can get good performance. That's a fantastic trick, right? And it's actually spilled over into the literature. You now see lots and lots of papers about performance of GPUs, of numerical methods on GPUs. Think about it. They've really smart guys at NVIDIA. Anyway, so think about how many papers have you seen about the performance of numerical codes on CPUs? It doesn't tend to be, the paper focus doesn't tend to be on the performance on CPUs. Every paper on GPUs tends to be about the performance, right? So there's a great trick that they pulled off, which was basically make these things hard as hell to program for, and people tried to program for them, okay? They've backed off recently. They've put back in cache structures that they took out in the original designs of the GPUs. The other thing which is also pretty clever is, in the 90s, we saw this ramp up in processor clock frequency. Basically, the number of operations that can be done per second went from megahertz to gigahertz to 2 gigahertz to 3 gigahertz. And then the manufacturers ran into, and they marketed these CPUs based on the clock frequency. So every year and a half, the clock frequency would go up. Every year, clock frequency would go up, or you'd have to buy a new PC, new CPU just to keep up, right? But eventually they couldn't, as we know, you've probably seen this several times already, they couldn't keep increasing the frequency, and they stuck at about 3-ish, maybe a little below 3. The GPU guys never played that game. They never marketed based on clock frequency. They took it up to a sweet spot around about 1 gigahertz, where the thermal dissipation was not massively, it wasn't really presenting a problem. And that's where the GPUs typically operate. They typically operate at about 1 gigahertz. Okay, so they played some interesting trade-offs and didn't necessarily fall into some sort of marketing arms race, which also skewed the development of CPUs. So if you look at an early CPU, you can see in this actual die shot, I think it's color-coded, but this is a die shot which shows you, in this picture, these are the graduate students. These are all the floating point units doing the work. We have a little bit of specialized cache, which is actually very specialized cache because it's kind of smart cache, which can actually do algebraic operations in its own. It's a texture cache which can do linear interpolation between two values out of memory. So although it's cache, it's also cache that's working. It's memory cache, which is basically bringing data in and doing some interpolation operations. So this whole thing is the graduate student. This thing, this orange stuff, this is the management. Okay? I think that's a better ratio. More graduate students, less administration. Professor's still somewhere else. Right. Okay? So, how did they do that? Well, how did they get rid of the administration? First of all, they nuked the out-of-order prediction. Right? So it's all more or less statically scheduled operations that get pushed through the GPU processor or the core pipelines. Got rid of the branch prediction. Again, statically scheduled. They got rid of memory prefetch units. They even got rid of the caches. But as I said, they'll put those back in later on because you can only do so much with ego. Right, so now that they've slimmed down this core, well, they've got more space. We'll put more cores on there. And again, we've got rid of enough management. Remember, in that original core diagram, we had about, what was it, a ninth? Maybe a 20th of the space was spent on the floating point units. We've got rid of most of the management, so we can then copy these cores because they take up much less space. So now we have, in this sort of simple abstract representation, we've got 16 independent instruction streams. That's 16 cores. Okay? But given its heritage, the CPU, those cores are very, very likely to be doing the same thing. They're probably going to have the same instruction stream. So what do? We get rid of a bunch of instruction units. So now the core design, and you'll recognize this as basically a SIMD device, where we single instruction, multiple data device. We're going to have one instruction unit, multiple arithmetic logic units, and some execution context. Okay? So we've got rid of quite a bit of management by getting rid of the branch prediction. Okay? And all that stuff. We're now going to get rid of more management by basically yoking a bunch of arithmetic logic units to one professor. Let's call this guy the professor, right? These are the graduate students. And he's going to tell them all to do the same thing, which isn't too far off the typical academic model, right? Okay? Or at least we better give each of the graduate students their own cubicle. So they'll each work on some set of registers as their own. We might want the graduate students to communicate together. So we'll give them some shared memory. Okay? So they'll have a scratch pad, basically. They'll have a whiteboard. They can communicate amongst each other. Okay? So we're building an archetypal research group. One set of instructions, bunch of actors, and the actors have their own storage space and some shared scratch space. Okay? So it's a little bit different than the original core x86 design. And of course, we clone them. So we'll take that SIMD core, clone it X number of times, as many times as we can, to tile the target size of silicon. So in this example, I'll have 128 parallel instruction streams, which are organized into 16 independent groups, 16 cores, and each core will be synchronized with 8. That's not quite right. It's basically, there's one instruction set being issued to each core, but then it'll be executed 8 times. Okay, is that clear? That's basically the architecture of the GPU. A bunch of cores, each core is a SIMD device. Now there are some issues. What do we do if your code has an if statement in it? Segfault, yes. We should disallow all if statements. That's actually rule number 1 for GPU program, don't if. Okay? Well, they do something called cheap branching, which is, let's say you have some non-branching code. Well, all the ALUs will just march along in time doing the stuff until they hit the branch. When you hit the branch, all ALUs traverse all parts of the tree. In this case, they'll go through both branches, right? You could take the red pill or the blue pill, but they take both pills. The threads that take the red pill, well, they all take the red pill. Some of them swallow, some don't, okay? Depends on whether they should be in that branch or not. So in this case, you have a flag, some local variable in the context of each of the ALUs. If it's true, then they'll do something. If it's false, then they won't do something. Okay? this is, of course, problematic because you've partially serialized your code, right? It's quite possible that only one of these ALUs would execute this piece of code. So you would have, in this case, 1/8 of the efficiency of the SIMD group. So avoid branching, if possible. It doesn't mean you have to go through, you shouldn't go through contortions of writing code to avoid ifs, but if you can do it in a fairly straightforward way, do so. Because of the way that the GPU is processing in these shackled SIMD groups, it means that if you have ifs, then you will have potential partial serialization. Now think about a code that's like a whole nasty nested bundle of ifs. Let's say there were 32 leaves in this tree of ifs. Then you have a real problem, right? Because all the code will traverse all of those branches. Yuck. Okay. The other thing that's going on is, and we'll see this later in terms of memory latency, we'll have this SIMD group marching in time, doing work on local memory on the device in the context of these ALUs, and then eventually they're going to request memory from outside of the chip. And they're all going to stall, because one of the problems with GPUs is that the round-trip latency for a request for memory, from data from off-chip memory, is now on the order of 1,000 clock cycles, roughly. Yes?
When you're talking about off-chip memory, are you talking about the memory that is on GPU?
We'll have some diagrams. So I'm trying to be somewhat abstract here. We'll just talk a bit about this as data that's not on the processing unit itself, the actual silicon chip. Okay? That's the longest round-trip time for fetch. Well, okay. So here's the problem. If all of these guys try to load some data from off-chip memory, it's 1,000 cycles. So you've got a gigahertz processor. So it's going to process at nanosecond scale. But it's going to be turned into a processing at microsecond scale. If every time that you want data, you're going to have to wait 1,000 nanoseconds, right? So the natural thing there in the progression of the GPU design is to provision each of the cores, these SIMD devices, with a good amount of context space, so register space, so that you can have multiple sets of data for these SIMD units resident on the core at any one time. Okay? So then the latency can be hidden by multiple contexts. And another smart thing NVIDIA does is they do hardware context switching. So it takes a fairly minimal number of clock cycles to switch between the ALUs processing one set of instructions and the ALUs processing a second stream of instructions. Okay? Or in terms of threaded programming, you could think of these ALUs as executing threads. Each one will have a thread. And as a thread stalls out, you'll switch those stalled threads out and then switch threads that are ready to compute in. Okay? Now, overall, that context, that thread takes longer to complete than if you had a cache that was doing a good job of predicting the data that was needed, to have it on hand, ready to process. You could be done as soon as up here if you had a really good prediction, really good prefetch, and so on. Okay? But the design principle of the GPU is we don't care when this thread finishes as long as the whole job is done in a certain amount of time, right? So it doesn't matter if threads stall. So we'll just swap them out, idle them out, and then bring in active threads that can do stuff. So let's look at this summary of the GPU architecture. It's a multiple cores. Each core has one, or more recently, more than one, wide SIMD vector units. That's those ALUs with single instruction streams. Each core has a pool of shared memory, so it looks a lot like the old shared memory machines that none of you remember. And each core can hardware switch between multiple contexts to hide memory latency. And unfortunately, branching code involves partial serialization, okay, through cheap branching. Okay, so that's an overview of what the GPU looks like. So once you've got that abstract GPU hardware model in mind, how do you program this thing? Well, it kind of has a natural, it sort of suggests a natural thread model, which is, again, you push some work onto the programmer. NVIDIA likes to push work onto programmers, okay? The programmer divides a compute task into independent work blocks. And the work for all those work blocks should be the same. Okay? The work block should be assigned to a core with sufficient resources to process it, because it's going to, so when you start up that subtask on the core, it's going to have to stay resident on that core until it finishes. Hardware context switching doesn't move data in and out of that core. It just changes which context the threads are working on, okay? So we'll see that a bit later on. And then each core is going to process the work block with a work group of threads, okay? So that's a lot to push onto the programmer. Not only are you going to make the programmer manage the memory hierarchy, which we'll talk about later, you also force them to design the parallel partition of the work and figure out how to push little pieces of the work onto these cores. So there's work. The work group is batch processed in subgroup of SIMD work items. So if you have a 32 wide SIMD unit, then your work group is going to be split up into groups of 32, which will then be batch processed through these parallel ALUs. And a thread is going to pass through a SIMD lane. Right? So there's going to be a specific piece of hardware that's going to manage, or it's going to process that thread's operations. We have to keep in mind that a stalling SIMD group of threads is idled until it can continue. It's going to block resources. It's going to block register space. And we're going to have to think about that when we think about how we're going to break up the work into these work groups. So this is kind of telling us that the work group itself can't be a massive part of the problem. It's going to have to be a small part of the problem because it's going to have to be resident in the core to be processed. Okay, more or less. Okay. The threads in the work group can collaborate through shared memory. And one of the big assumptions is that each work group is going to be basically the same set of instructions. It's the same program for each work group. And the work groups themselves should be independent. So if we think about mapping it back to this device, this abstract device, where is it? Here we go. Each of these is an independent core. There's a scheduler that's going to push tasks to each core, but you've got no guarantee in which order those tasks are going to be pushed by the queue manager that's going to manage and push the task to each core. So all of these work groups that work blocks that you're passing to these cores should be independent. The data outcome for this for a work group that's processed by this core should not influence or be dependent on the outcome from this core. Okay? So we need to figure out ways to do an embarrassingly parallel partition of our work. We're going to have to find that embarrassingly parallel partition in order for an application or part of an application to really map well onto the GPUs. Okay? Okay. Why do we care? Why are we going to knock our heads against this problem? Coming up with partitions, managing memory, and doing all this hard work. Well, you can look at trends. Here's the top 500, top 15 or so. And I've just highlighted the ones that involve accelerators. In blue, that's Intel's accelerators. The ones in green are NVIDIA's accelerators. Where the high-end supercomputing market goes, we follow. This is, the trends tend to trickle down from on high. This is a trend that we'll have to pay attention to. If you look at the percentage of actual systems that have accelerators, well, 87% of them don't have accelerators. But that, 13% is delivering about 35% of the actual performance, which is interesting in itself. Okay? Any questions about that? I've stayed abstract until this point. I've tried to give you the sort of vendor-neutral viewpoint on what a GPU is. It's a set of cores. Each of those cores is a wide SIMD unit, okay, with a limited number of instruction streams and many more compute units than instruction streams. Okay? Any questions? Okay, cool. Right, so let's drill down a little bit into specifics of NVIDIA's, the NVIDIA world. First of all, CUDA, I think they stretched to figure out an acronym for CUDA, Compute Unified Device Architecture, which basically means they needed some words to spell CUDA. Okay. I have some problems with the terminology that came from the graphics part of graphics processing units. It's laced with terminology derived from weaving, like warp, thread, and texture. Okay? And it's a completely broken analogy for parallel computing, because I actually happen to live with someone who weaves. She has her own mini loom, and she demonstrated it for me. And although there are multiple parallel threads, the processing, which is the weaving, is an entirely serial process, because you put a shuttle and you roll a shuttle from this side to this side, and it's entirely serial. So it's the worst possible analogy for a parallel processor. Okay? It's got the notion of data parallelism, but the actual processing is serial, which I find entertaining. Okay. Right, so instead of talking about warps and textures and such, I'll talk about thread arrays. I'll put up with thread, because that's a fairly universal terminology, and SIMD groups. That's basically threads that are marching in lockstep, managed by a single instruction stream. Okay. Just in case you don't know how these GPUs are structured, here's a GPU from a couple of years ago. It's an NVIDIA GTX 590. It is a daughter board or coprocessor board, which in this case will slot into your PC motherboard through a PCI Express slot, which is this gold-plated thing here. Okay, this original model was a PCI Express 2 interface, which I think had a bandwidth of about 6 gigabytes per second. So we can move data on and off this device at around about 6 gigabytes per second. And we'll see that's not very much in the grand scheme of things. That's 6 or actually 7 CDs a second, but that's really not very much. Okay? The modern cards have PCI Express 3, which is about double that bandwidth. So we'll call this thing, this whole board, we'll call a device. In actual fact, this will be 2 devices because this is an odd board which has 2 GPUs on it. Okay? All data, including programs, for this quasi-independent processing board have to travel over this interface. All data that you want this thing to work on has to travel over this over this interface. All results have to be pulled. If you want to inspect the results, they have to be pulled off over this interface. Okay? So you should think about this as basically a computer on its own that we communicate through this bus. This thing has 2 GPUs. And it has its own set of memory chips. Okay? In this case, we've got 2, 3, 4, 5. Looks like 5 memory chips each. About 1.5 gigs each. Okay? Recently, GPUs have been scaling up. You can get to, is it 12 gigabytes now, I think? Maybe more. I can't remember the latest specs. Stopped paying attention after a while. But that tells us something. There's a couple of things we've learned so far. One is that we've got a relatively weak link to the outside world through this PCI Express interface. So the ideal model for computing one of these things is copy a relatively small problem which can fit into the memory on the device, let's say about 1.5 gigs, leave it to process that for as long as possible before inspecting the results by bringing the results back over. Okay? These things are independently powered. There is an upper limit on how much power these GPU boards can draw, driven, oddly enough, by the interface standard, the PCI Express interface standard, which says you shouldn't power this thing up to several gigawatts because this will fry everything. So there's an upper bound limit, which I think this may actually exceed, but it's around about, I can't remember the details now, about 300 watt limit on how much power this card should draw. Some cards exceed the PCI limit quite a lot, so they actually have 2 settings. They'll have a little slider switch, which is the setting where the card draws less power than the PCI limit, and the brave setting, where you can ramp up how much power this thing will take, but don't complain, right, when it fries. And if you can get, so there are literally hundreds of GPUs now. If you want to get the specs on the latest versions of the GPUs, you can actually go to the NVIDIA GPU wiki and you can get things like the amount of memory and number of those cores, the number of floating point units, the peak bandwidth, the peak floating point performance, and so on and so on. There's like hundreds of different ways of measuring these devices. Now, these GPUs plug into your typical motherboard. Here's got an example from a sort of experimental machine we have. You can see the RAM. You can see the CPU is buried under a huge heatsink, and the heatsink has its own fan. So I would say that both Intel and NVIDIA have issues with cooling. This is just, it is the biggest issue that we're all facing going forward. It's not unique to GPUs. Inside the GPU case, you've got a cooling fan, or possibly a heat exchange, which uses water cooling to duct the heat away. And there you can see the power cables are plugged in to power these devices. Okay? We'll call the motherboard the host, and the card will be called the device. Okay. Now, GPUs are I have to say, rather unbalanced devices. Here's an actual example. This is an NVIDIA Fermi-based card. So the chips have gone through this. This is the slot. Here's where the chip would be. The chips have gone through several generations. Let's see if I can remember all the generations. There was the ones before they decided to start naming the chips after scientists, and then there are the scientist generations, and we have, I think, I can't remember if the first generation was Tesla, but there's Tesla, Fermi, then it's going to be Kepler, then Maxwell, which is the current generation. The next generation was going to be Volta, but nobody had heard of Volta. So, and they also had some design issues, so they've progressed into Pascal. So not only scientists, but mathematicians. Okay, so here's an example of the Fermi class. And here we can see a block diagram. And it's rather indistinct, but interesting. So each of these is one of those, they call them streaming multiprocessors, but this is marketing speak. This is a core. And it's a core with 32 wide parallelism, I think. And interestingly, by the time they get to the Fermi generation, they've put the L2 cache back in. They've also put L1 cache in there. So there's L1 cache on the core, there's L2 cache on the device. And you can actually see this little, it's a little indistinct. You might see it better on your, if you've downloaded the PDF. But this is Intel marketing material. So they call each of the arithmetic logic units here a core. We know that's not the case. A core would have its own instruction stream. There's just one instruction cache and two warp schedulers, which basically means two instruction streams. And I started to relabel every one of their cores as an ALU because I was feeling pissy. But then I got bored, so I didn't do that. But basically, these are all arithmetic logic units ganged together in, I think, 32 wide SIMD units. They also have some special function units. And what is that? That's for 128K of register space and 64K of shared memory. Okay? That seems like a lot, but it's really not that much register space or shared memory space, because you take that amount and divide it by 32, and those are the resources available to a single ALU. Okay? So we want to have multiple threads available to each ALU. So because we want to hide memory latency, we want to have register space and shared memory space for multiple threads per ALU, so that we can maximize hiding of latency. Okay? So that 64K gets divided by 32. Well, the registers file gets divided by 32, and then gets divided again by the number of threads that you really want to have resident on that, or available for that ALU to process. Okay. The other thing that's going on is that the bandwidth between this processing unit and the memory, which is on board, is roughly 200 and, what was it? At this point, it was about 100 and, I can't remember now. It must be about 200 gigabytes per second. So you can move data between the memory and the device, the processor, at 200 gigabytes per second. That sounds like a lot. But you've got 15 or 16 clusters of 32 floating point units. So again, if you start dividing that bandwidth by the number of floating point units, you find out that in order to get peak performance of about 1.4 teraflops, you would have to be doing, I think I worked it out, at about 28 flops every time you load or store a single floating point unit. There are very few computational problems that basically require you to take in, to do that, have that kind of algebraic density. Okay.
So
yes?
each
you worked it out how much should be the bandwidth in order to get to be able to transfer back and forth and to actually keep that rate?
Right, so the bandwidth is the manufacturer specified bandwidth, which is 200 gigabytes per second.
Right, but what it should be in order?
Oh, lots more. Right, if I wanted to...
If you want to keep that rate of 1.4 teraflops and then keep transferring, how much bandwidth you should need?
I'm talking about on-device stuff, so I'm not even talking about the host. I'm just everything's on the device. And you can just scale up 28 by, if you wanted to just do 10 floating point operations or 5 floating point operations per load store, you would just multiply that by that ratio, right? Okay, so for the rest of the talk, I'm not really going to talk about the peak performance, because the peak performance almost falls into the category of unobtainium. It's really typically very, very hard to get towards these peak. There are some operations you can do. Matrix multiplication on very large matrices that will actually fit on the device and are large enough to generate a large amount of floating point operations you can do. Generating fractals or other weird corner cases where there's just an unbounded amount of floating point work and no input data and one output data. There are also weird corner cases where you can get really good performance. Typically, people don't see this type of performance out of these cards. But we can see a pretty good performance, but not typically the peak floating point performance. So that was the previous generation, the old Fermi class GPUs. The latest, and it was already a pretty massive parallel device with 16 times 32 ALUs. The latest one was a real monster. It's the Kepler class device. And it has 15 cores. Each has 192 floating point units. Now, that sounds like an upgrade. But there are some things that didn't really get upgraded. So we went from 32 floating point units to 192 floating point units in a generation. But the register file, it doubled. So you have 6 times as many workers, but only twice as much worker space. The shared memory stayed the same. This is problematic. So what's going on here was actually the Fermi class was, in some sense, the design was informed by the emerging notion of using GPUs for real-world GPU, general purpose computing. Okay? But that's not where NVIDIA makes its money. So their performance as graphics cards wasn't very good. So the Kepler class is the swing the other way, where this is a device designed more for the graphics part of the business, which is the rendering part of the business, where you want massive parallelism at all costs, and the rest of it's not that important. Okay? Now, the peak performance would be 4 some teraflops. Yay. But I think we can quickly figure out that the number of floating point operations you'd have to do per load store would be pretty immense just to get that peak performance. So it's, again, not a really realistic, peak performance. So let's look at this, the progression in the, they call them streaming multiprocessors. The SM architecture has gone from being 2 8-wide SIMD lanes to 3 8-wide SIMD lanes to 32 floating point units to 192 floating point units. We can all see where this is going, right? Well, more floating point units must be better, so you must expect hundreds and hundreds of floating point units. Well, this isn't necessarily a scalable way to scale up the device. Everybody who lived through shared memory machines in the 90s recognizes that there's basically an upper bound on how many compute units you can attach to shared memory, which is really going to limit how many floating point units they're going to cram onto a core. So if we look at the transition from Kepler to Maxwell, Kepler had 192 floating point units, all talking through 64K of shared memory, while Maxwell, they've partitioned again. The core is now sub-partitioned into 4 mini-cores, okay? So eventually this thing's going to look like a fractal in the diagram, right, as they keep having to repartition at multi-levels. Okay. So they've partitioned the register file. Of course, they still haven't partitioned the shared memory, which is interesting, which means that if your threads have to collaborate through shared memory, that's not going to necessarily work very well. Yes?
So what was the number you mentioned on the Fermi versus Kepler for the, you had, I think, flops first, and then you went G floats?
Giga floats. That's giga floating point numbers loaded per second. Yeah. So I'm drilling back down into the cores at the moment. Okay. This has been the trend and progression in their architecture. But what's really fascinating is that the CUDA model for programming these things hasn't changed substantially in the core way that you program them. Because of this idea of partitioning the work into work blocks, which get processed by work groups, and the work groups themselves consist of threads, and those threads get SIMD batch processed, that has scaled. At least we've started using G80s, Teslas, Fermis, Keplers. We've used all of those, and more or less the same code is still working. Be interesting to see how well it does on Maxwell. My codes are still working well. So the thread model itself is actually more interesting in the way than the way they're organizing the floating point units on their devices. Because even though we wrote code 6 years ago for this architecture, using their thread model, it still works today, even when they've upgraded. Now, overall, the performance in terms of percentage of peak may not be ideal, and we might still have to tweak for the latest architecture based on some understanding of the organization of memory registers and so on. Then we still can run that code, and it still gets pretty good performance. Now, the roadmap, I apologize, it's still dark. Starting down in Tesla, we're plotting, in fact, this is something on the vertical. It says SGEM, single precision general matrix, matrix multiply in some scale, which isn't determined. This is basically marketing from NVIDIA. We're at Maxwell right now, more or less. We're moving to Pascal within the next few years. Pascal's interesting because along with Intel, NVIDIA, and likely AMD, everybody's moving to stacked memory, which will help with some of these latency issues to some extent. It will also help with bandwidth. But I think they may be being very optimistic about this. We'll see. Yes?
The differences you talked about between Kepler and Maxwell is for Kepler K20 and 40 or one?
Right. So this is, these are the K model cores, the SMXs. This is at the level of the architecture of the core. And moving to Maxwell, we'll start using this different.
Yeah, but Kepler is K20 and K40.
Yeah, but there's also a whole bunch of other Kepler devices. There's consumer cards, there's all sorts of, you can even get it in your laptop if you want. Okay. Yeah, but the ones starting with K, they're the Keplers. Okay. So Maxwell's not really even fully through its design cycle, but they're already projecting Pascal. Pascal will use stacked memory, and this will help improve memory latency issues. I'm not sure exactly how they're going to cool this thing. They're also going to move away to some extent from the standard PCI Express interface, because that's also a rather problematic bottleneck. And they'll be using actually their own interface, which in itself could cause problems. Okay, so let's just look at sort of, I threw some numbers together to give you a sense of the memory hierarchy in these devices. So on chip, they can move data around, data around between registers and so on at about terabytes per second. Between the chip and the memory on the board, it's about 300 some gigabytes a second now. Between the board and the host, it's about 16 gigabytes per second. And then Intel's bandwidth is a moving target. It's hard to pin down, but somewhere on the order of 25 gigabytes per second or more, depending on how much you want to spend. But that's incredible range of bandwidths. What this really says is move your program, your data, a small amount of data as possible, onto the device, leave it there for as long as possible, and pull off as little as possible. Now, in the numerical PDE world, that basically is not particularly bad news if you've got a method with relatively shallow halo regions. So finite difference methods, finite element methods, finite volume methods can be quite well suited to this because you've got a blob of your domain and then the surface area you might need to communicate. But in terms of the overall data, that may be quite a small fraction of data. And we've found that this bottleneck here has not necessarily been a real problem for us. Okay. Right, now to learn more about CUDA, Google CUDA, or just go to NVIDIA's webpage. You can get all sorts of documentation and download their developer kit and so on. So let's talk about the CUDA data flow. In CUDA, you, the programmer, and remember I said that NVIDIA pushed a lot of work onto you guys. You, the programmer, are in charge of explicitly moving data between the host and the device. We have to remember that the device and the host are asynchronous. Basically, you're getting instructions that are getting issued by the host. They're queued up on the device. They're not going to be executed immediately, so you have to keep that in mind. So we can queue up some data to transfer to the device. And to do that, we're going to use the CUDA API. And there's a useful function called CUDA memcopy, which is like the memcopy. It's CUDA memcopy, which will copy between the device and the host and the device. In order to copy data onto the device, we need to allocate some space for that data. We'll use CUDA malloc. So now you can think about these things as having separate memory spaces. NVIDIA spent a lot of time trying to, well, first of all, partitioning the data spaces so that we have a memory space on the device and a memory space on the host. But then when we moved to 64-bit, they spent a good deal of time in marketing trying to sell you a unified memory space. But I actually prefer thinking of these things as having distinct, separate memory spaces. Because we don't want to treat this memory as just part of the memory on the host, because if you do that and you're a lazy programmer, you'll just keep moving memory backwards and forwards. I always think of this as a distinct device which we move data to, instead of just sharing a pool of memory with the host, because that's a dangerous way to think. Okay? So we can allocate memory on the device with CUDA malloc. We can then CUDA memcopy data from the host to the device. And then we can queue a kernel task, and we're going to label the task that's performed by each thread executed on the device as the kernel. And then we can CUDA memcopy the data back from the device to the host. Okay? That's the archetypal model for all CUDA computing. Now you just have to fill in the details. Right? So first, CUDA malloc on the device, CUDA memcopy data from host to device, queue the kernel on the device, and then CUDA memcopy the data back. Okay, any questions about that? And just remember that even though you say do it now, it's basically like a non-blocking CUDA, a non-blocking MPI operation. Basically, you're just queuing up something to get done on the device because it has its own agenda. And here is hello world CUDA style. This is what the piece of code that gets executed on the device, on the host. So here I'm going to take an array. I'm going to prepare an array on the device. I'm going to invoke a kernel on the device, and I'm going to read the results back. Okay? So it's pretty much like Hello World. We're getting it to give us a message back. The device will give us a message. In this case, I'm going to allocate 512 floats. Okay? Now, CUDA uses pointers. They decided, basically, because I think they had a long-term vision that they'd have a unified address space, that they would use 64-bit pointers, which would be valid for host or device. Some number of bits would give you where it is in the host device world. So the handle for a CUDA array is just a pointer. Okay? So CUDA malloc is going to basically set the value of that pointer to be a pointer that's valid for the device. I really discourage treating that like a host pointer. Don't try and dereference that pointer from the host. Okay? You want to treat it as dangerous. Never dereference that pointer on the host. Now, next thing you need to do is decide what is the partition of the problem. Here I'm going to fill entries in a vector, linear vector. I'm going to set all the entries to some value. Okay? So I'm just going to do something very simple. I'm going to tile that vector into groups of 512. Now, this is unfortunate because I've just realized that the vector is length 512. I divide by 512. How many groups do I have? 1. That was very stupid, wasn't it? Hold on. Okay, so now we have a vector, 2,000 entries. We're going to tile it into groups, tile it into sections of 512. And each of those sections of 512 will be sent to one core, or sent to a core. Okay? So if this device has 4 cores, it could handle those 4 sections independently. It's just going to put a value in those entries. So that's an embarrassingly parallel task. There's no communication needed between those cores. There's nothing complicated that's going to have to happen. There's no, even the floating point units don't need to communicate. I'm going to keep walking backwards and forwards and make his life very difficult. Okay. Now, we were lucky here that we chose a multiple of 512. Right? I'm going to be awkward and say that. So I'm going to say some vector of length 3789, and 512, I happen to know, doesn't divide that number. Okay? So we have to decide on a number of tiles that are going to tile this, how we're going to split it into units of 512. So this is why we have that awkward n plus 511 over 512, which I put it up there. It's a stupid way to do this, but this is prevalent in CUDA code. You'll see it everywhere. Why do we do this? We just basically are rounding up to the number that will give us enough so that enough tiles so that we'll tile this with 512. So that will be, what, 7? Does 7 work? Roughly. So it'll tell us 7 tiles. And then inside the task for the thread, we're going to have to check to see if we're making a valid write to this array. Okay? Because we'll have extra threads in a tile that's only partially needed for the tail of the vector. Okay? Everybody understand this formula? Good. Okay. Right. And then, the other thing is that we're creating a dimension array, or set of dimensions for the block, which will be the block of the work block that gets processed by each core, and then the grid, which is just the array of blocks. So we want to say how many blocks we need, what size of the blocks, and how many blocks do we need. Then NVIDIA uses an extension to C++. Yes, hello.
Why 512?
Random. I could have chosen 17. Let's do that. 17, and then what would this be? 16, and this would be 17. Or if I was actually programming properly, I would say something like block, which would be 17. I'd say I want the block of size that, and then I'd say something like this. And we're just using quirks of integer division to give us a roundup to give us a sufficient number of blocks that tile this vector of length n. So we've done something quite subtle there, and it's something you don't necessarily think about yet, but we've done the parallel partition of our problem. Actually, we've done something a little bit more insidious. We've decided on a map between a parallel partition or a parallel thread of an array of threads and some work. We've kind of already in the back of our minds, we're thinking we're going to tile up this array into sections, and then we've decided that each thread in that block is going to do something to one entry in that block, okay? So NVIDIA's CUDA C is an extension to C, so mainly so that it could throw things like this in, which is kind of looks like templating, kind of. It's not templating, kind of. But what we're saying is we're going to execute this kernel, which is specified somewhere else in the file, with this many blocks, and the blocks have this size. Okay? So that has specified the array of threads that will process this kernel, this function call. This function will be executed by this many threads in this many blocks, or this many threads in this many blocks. Okay? And then we pass in arguments as you'd expect. Notice we should only pass in device pointers to the device. It's pretty stupid to give it a host pointer because it's in the wrong, really in the wrong physical memory space. Now, once we've actually just queued that up, but we're going to do a CUDA memcopy, which is a blocking call. It'll block till all the tasks that have queued up on the GPU have finished, and then we will copy from the device to the host. Notice I'm using some little trick to remind me which of the variables live on the device, which live on the host. D underscore for device, H underscore for the host. Some people call it C underscore for CUDA. So you'll see that in the literature too. Okay. And then we have to specify which way we want to copy data, because it's not smart enough to decide that this is a device pointer or this is a host pointer, so we specify CUDA memcopy device to host. And then when the data's on the host, it's a block until it's on the host, and then we can print out the entries on the array that have arrived on the host. Does everyone get that? That's basically, do you have a question there?
You pass n to the kernel?
Yeah, so that's the exception. So n is passed by copy, that's okay. So technically all these things are passed by copy, so that's fine. It'll just be a variable copied into the kernel. Okay? Okay, so let's just iterate. We allocate space on the device. We design a thread array. So really, these are not independent. The way that you write the kernel has to tally with the way that you specify your thread array. So the specification of the thread array and the kernel code, which we'll see in a minute, can't be independent. You're enforcing assumptions through the specification of the thread array. We queue the task on the device, basically compute that stuff, and then copy the result back. Those are the archetypal steps. Typically, there's another step, which is you copy data onto the host. But we just kept this simple. So let's motivate this. I'm going to depart a little bit from the standard presentation of CUDA. For my own selfish reasons, we'll see later on in the day. So if we motivate what that function that's going to fill up the vector would look like in serial, you would have a for loop. You would say, loop over the entries and set them one by one, right? That's pretty clear. We all read C. If you're Fortran, you know how to mutate this into Fortran. Okay. Now we're going to think about the tiling. We've already sort of established we're going to tile this problem just by the way we designed that thread array. It was natural to you when you think of tiling or partitioning that array, but we're now going to think about that. How does this going to affect the loops? So if we think about n as our global index, we're going to partition it into a double index, double nested loop. The inner loop will loop over T for thread, and the outer loop will loop over B for block. Okay, nicely color-coded. We can get from the thread number and the block number to the index number just basically by saying thread ID plus 4, which is a number of threads in a block, times the block number. Okay? I can get just a linear mapping from here to here, from here to here, just by taking offsets based on the block location and the thread index in that block. Okay, so we'll write it out in actual code. It's still serial code, but I'm starting to mutate this towards CUDA. Okay, so I'm going to loop over the blocks, and there's going to be grid dim number of blocks. I'm going to loop over the threads in the block, and then each thread, and I mean thread really loosely here, this is basically just the thing you get to do in the inner loop, can reconstruct its location in that global vector by something we've arbitrarily constructed, a map between the thread block indices and the vector index. Now, we do have to guard against the case that in case we're one of the redundant threads, which is the saddest thing that thread can be, which is the leftover thread at the end of the end block, right? In our case, we're 3,168, 79 threads. They didn't tile neatly into 512s, so the last thread had some subset of those which were going to actually do something to the vector. And then you have these sad guys at the end, whose job is basically do nothing, right? It's the saddest fate through a thread. So each thread has to check to see if it should do something. Now, I told you not to if. This is kind of the exception because we have to check to see if we're a good thread or a bad thread, right? But it's not a particularly deep if. But it does tell you that some of the threads in the SIMD groups are going to be doing nothing at this point. Okay? So this is entirely serial. We haven't gone parallel yet. Is that clear? We all got it? Any questions? This is the pivotal thing where you're going to collect the things that we talked about so far. We're partitioning, doing work partitioning. We're doing it in an embarrassingly parallel way. There can be no loop carry dependence between this block and this block. So for instance, if we were scanning along and adding up these entries, we couldn't have done this so easily. We'll see an alternative way for doing that later on. So this inner block, there can be no dependencies between different Bs. So B0, B1, B2 should not change, should not depend on each other, those loop iterations. Okay? So there we go. Now I'm mutating again to match up with some really crappy CUDA naming conventions. So here we have grid dim and block dim, which are basically just upper bounds for those, for the tile and for the group of tiles. But now we're going to use indices, which are the indices that, this is the convention that CUDA uses. Block ID X is going to be a dim3, and it's 3 integers, or whatever it is, that indicate which block you are in a 3-dimensional array of blocks. Okay? We just happen to have chosen one axis to work on. We're doing a 1-dimensional block array. We could have had a 3-dimensional block array, but let's think 1-dimensional. But this explains why we're taking the X index out of this block index. Similarly, the thread index can be a 3-dimensional, or the thread array on the block can be a 3-dimensional block of threads. Again, we're just choosing one axis to work on. The upper bounds, the dimensions of the block and dimensions of the grid, again, are 3-dimensional dimensions. But we're just choosing one of those dimensions. We could have chosen multiple dimensions. And then to get from the thread index and the block index and the block dimension, we can then reconstruct the index into the array, just as we did. So basically, take everything on this slide, add .x to the dimension, use stupid variables for the block index and for the thread index, and you get prototypical CUDA code written out in serial. The kernel for CUDA is going to be this piece of code. These for loops will disappear because they aren't processed in a sequential fashion. Each iteration in the for loop gets assigned to a thread. In this case, this inner for loop gets assigned to a SIMD lane and done in parallel. Each outer index, this block index, will be the index for a work group. Okay? So that stuff will just disappear. And just for completeness, I've put in the thread index notation. I don't expect you to absorb this straight away. Just when you see thread IDX, you think thread index. When you see block IDX, block index, yes.
Can you go to the previous slide?
Sure.
One more. Is there a reason we are doing pre-increment or post-increment? I mean, plus plus t, plus plus.
Oh, I just like that.
Oh. I mean, it's not a requirement from CUDA.
No. This is just me being lazy. It should be noted that the block indexing used to be a 2-dimensional block array, but now it's a 3-dimensional block array. Right. Oh, and the other thing is that the thread index X is going to be the fastest index. We're going to have to actually think about the ordering of the threads in the thread index array for the block, so we'll think about that, but it'll come up later. But the X is the fastest index. Right. There is just an ungodly amount of information available on the properties or the characteristics of CUDA, and CUDA has evolved in several iterations. I've been using up to, I started with 1.0 and gone up to 3.5 and barely paid attention to any of this. But some of the limits on how many threads you can have in the thread block and how many blocks you can have in the grid have actually changed over time. So they tend to get larger, more threads per block, more blocks per grid. That's basically the outcome now. Right. So the CUDA kernel basically is the payload at the inner part of that nested loop structure, where we've lost those for loops because the for loops are handled by parallelism. Right? And I kind of take you through that step-by-step approach because I want to sort of explain what those thread index variables are. You can think of them as the loop variables in parallel for loops. Okay? The inner for loop is handled at the level of the core. The outer for loop is handled at the level of multiple cores. Okay? And this explains, and this has been the hardest time. I've been teaching CUDA for as long as I've been using CUDA, 6 years, And this step has always been the hard thing for people to understand, is where the hell do these variables come from? They are intrinsic CUDA variables that are supplied to, or basically the compiler will insert in code to actually give each thread knowledge about its rank, and its rank is a 6-dimensional variable. We've only used 2 of those dimensions. But in the MPI terminology, this is how we determine our rank, and it's in a 6-dimensional space. 3 dimensions for the thread block, 3 dimensions for the array of blocks. Okay? Once you know that, you're 90% of the way to proficiency in CUDA. The last 10%, that's hard. Right. But this is the piece of code that gets executed by every thread. Right. Any questions about that? Let me just reiterate. So really, behind the scenes, there's this. Double nested, or in fact up to 6 nested serial loops which get parallelized, and you just express what happens inside the for loops that are implicitly described by the thread array. And that's why I say that when you specify the thread array, you're actually already coding the kernel, because they're intimately related. Because as you specify the thread array, you've already you've already designed the workers, and then the kernel has to use those workers and decide what each worker does. And implicit in this decision was, how do we make an embarrassingly parallel partition of our serial for loop? And we were lucky because this is a linear map of index to entry in the array. So that's something that's embarrassingly parallel, and we can partition at will. Okay?